I'm going to talk about two sets of applications that we're developing as part of the Crossroads 3D FPGA Academic Research Center. Probably don't need a lot of background here if you've been coming to these talks. The Crossroads Research Center is combining researchers at 3 universities with 7 PIs and dozens of students. And some context for me, as opposed to all of these other people, I'm the only person here who's in a computer science department. I'm the software person. So as opposed to the very hardware, physical, system-centric view that you've been hearing about from these other people, I'm going to give you a software person's view of what Crossroads is really all about. And in my mind, Crossroads is all about applications where data is on the move. When I talk about data on the move applications, here's some examples. A hypervisor hosts multiple virtual machines with a virtual network instantiated between VMs. As the data traverses between different virtual CPUs, filtering and firewall policies are applied to the data. So in a data on the move application, we're providing functionality that's sitting between other endpoints that are doing what we usually think of as the application layer functionality. Here's another example. A distributed machine learning framework is designed to classify images. Images are coming in over the network, compressed and encrypted, and they must be decompressed or decrypted before they're passed to a GPU for classification. So here we would think of the endpoints of processing as the GPU doing the classification, or the client application that's sending in the image to be classified. But the sort of hidden application that's operating over data while it's flying through the system is this decompression and decryption algorithm. And as a third and final data on the move application, we can think of a long-term storage system that's re-encoding data on an FPGA using erasure codes to add redundancy before writing data from network to disk. So once again, there's some application that's writing data to the disk. From a programmer's perspective, we're really just thinking about the application and the disk. And yet there's this hidden intermediary application in flight that's doing the re-encoding for us. Now, data on the move applications are driving change all over the system's landscape. We see things like distributed machine learning, network functions, machine learning, and data analytics, shipping data all over the place. And alongside this data that's being shipped from endpoint to endpoint, we see an increasing use of heterogeneous compute platforms trying to achieve high throughput, and that the data is distributed across multiple nodes, and the data is physically moving through networks and disks and memory. Now, these data on the move applications are pushing right up against what we think of as the traditional server compute model. In a traditional server compute model, that is, your off-the-shelf server hardware, the pizza boxes I have stacked up in my lab, the server is designed with the idea that the data is going to dwell on the CPU as much as possible. And so the implicit assumption here is, first of all, that the processor is a one-stop shop. There's no need for other compute platforms like GPUs or FPGAs. The processor is going to do all the work. And the second assumption baked into our architecture is that I/O is rare. Data isn't moving off and on the processor because all of the work is happening on the processor. And really the CPU is king. So let's break this down and see why this model isn't coming together with these data on the moves application. The idea that the CPU is a one-stop shop and there's no need for other compute platforms is falling apart, primarily because developers want richer models of parallelism. So that can mean that they want the benefit of other processor architectures. That is, they want deeper and more customized pipelines or wider data parallelism. And it can also mean and that they need heterogeneous compute, or it can just mean that they need more CPUs and that they're shipping things out over the network, which leads to our second assumption that I/O is rare. The assumption that I/O is rare and we shouldn't worry about optimizing it is only true if your data is sitting on one CPU and that's where it lives. But in practice, modern applications are pushing enormous amounts of data in and out, to and from network and to and from disk. And so data is actually constantly arriving and departing. And so IO is the norm. Now, we've seen some very gradual changes in server architectures that recognize that IO is the norm in the form of DDIO and kernel bypass. So these are changes to both the software and hardware architecture that are trying to speed up IO performance. But really, even with the benefit of heterogeneous compute, DDIO, and these small changes, data on the move is not particularly well supported by today's server architecture. So if we have a CPU-centric architecture, when I have, let's say, a packet coming in off of the network that needs to be processed by some other compute platform, not the CPU, let's say it's the GPU. One option for our design space today is to stick with a CPU-centric model. And so this is what we typically see today, where data comes in over the network, and then it maybe goes to the CPU, and then it bounces to the GPU, and then it comes back to the CPU, and then it's shipped out over the network. And maybe the CPU is doing some modification or processing over the data in between the network and the GPU, or the network and the accelerator that it's attached to. But this data is moving around so much. This leads to increased latency and throughput bottlenecks through PCIe or whatever interconnect you're using. Furthermore, it's wasting your most flexible compute resource, that is your CPU, for boilerplate, bulk, and parallel compute. So these data on the move applications that I talked about are doing things like encryption, compression, things that are embarrassingly parallel. And I'm going to note as an aside that these are things that the FPGA is good at. Another trend we're seeing today to better support data on the move, that once again, I think is a very incremental step, is to use FPGAs to implement some of these data on the move applications in smart endpoints. So what does that look like? That looks like we have smart disks, smart NICs, smart memory. And what you'll see in these systems, if data comes in, from the network and then needs to be processed by a GPU, and there's some encryption or some acceleration or some other encoding that needs to happen on the data in flight, that hardware vendors will attach a little FPGA to the accelerator, and data will come in. It'll still go through the CPU, and then it'll hit the FPGA in flight that's attached to your memory or your disk or your GPU, and then it'll be processed there. There are a couple of problems with this architecture, though. First, the data still has to go through the CPU to get to the endpoint. But second, the resources you have in the FPGA are fragmented. You've limited your processing that you can do over data on the move to data that's on the move headed to a particular endpoint. I can use an FPGA attached to storage to handle that example I talked about, where I'm re-encoding data with erasure codes to store onto the disk. But I can't reuse that same FPGA that's attached to the storage to accelerate my networking. I've divided up my FPGA resources and stuck them in places that they're really only useful for one application. So this is where the Crossroads FPGA comes in. It offers new opportunities to support data on the move applications. And what we envision is that there's one large, highly provisioned Crossroads FPGA, you'll see it called Nexus here for legacy reasons, Crossroads FPGA that sits at the heart of data movement throughout the server. And any data that's coming in off of the network can be processed, or coming off of the network, or coming between CPU and disk, or coming between CPU and GPU, can fly through this FPGA and receive processing. Benefits here are that we can have the best FPGA parallel, highly pipelined streaming application performance. We know that in practice, FPGAs are often even better at these tasks than traditional CPUs. But just sort of in terms of where data is moving in the system, we're avoiding the bottlenecks and latency overhead of bouncing between many compute endpoints, because the FPGA is naturally on the data path between the compute endpoints. If I want data coming through the network to have TCP reassembly applied to it before it hits the application layer, the data doesn't have to go anywhere new. It doesn't have to be copied. It doesn't have to go over an extra communication channel to get to that FPGA, because the FPGA is already at the heart of the server. Furthermore, compared to the smart FPGA, smart NIC, smart memory approach, the Nexus FPGA doesn't have the fragmentation problem of smart embedded hardware. It's useful anywhere. So today I'm going to give you examples of two applications that are going to benefit from the Crossroads architecture. And I'm going to talk about how these applications are a little bit similar in the way that they use the FPGA, but they're also different in that some of them are CPU-centric and some of them are FPGA-centric. And I'll talk a little bit more about what this means, but at a high level, a CPU-centric application is one where the developer spends most of their time writing software that runs on x86 and thinks of the FPGA as an offload, something that's here to help out. And an FPGA-centric or FPGA-first workload is an application where the developer spends most of their time writing RTL and thinks of the CPU as just a helper there to do a little bit of offload or special case programming. So within the Crossroads Center, there are a bunch of teams. You've already heard from folks who are working on their programming and configuration teams. But today I'm just talking about the applications and these data on the move apps that are benefiting from the Crossroads FPGA. So today I'm going to talk about two sets of systems. I'm going to talk about the Pigasus IDS and the Norman operating system. For the machine learning applications, I'm going to refer to the talks by my colleague Vaughn Betts, who's an expert in accelerating ML using hardware. And instead, I'm first going to give an overview of Pigasus, then an overview of Norman, and then we'll do a very brief recap to compare and contrast how Pigasus and Norman use the FPGA and what future work is in store for these projects. Okay, so Pigasus. Let's talk about a specific application. Let's talk about intrusion detection and prevention systems. So an intrusion detection and prevention system is a system that's deployed at the gateway of your network, that is between the internet and your enterprise applications, to identify network threats. And the way that identifies network threats is by checking packets, including their payloads, that is their contents, against complex rules. Now, in order to inspect payloads, the intrusion detection system therefore has to look at every byte of every packet, and it needs to do so by looking at those packets in order, the way that they would be analyzed by an end host application. So if packets are dropped or reordered by the network, the intrusion detection and prevention system needs to reorder them and then scan through all of that byte stream that the application would see. So this is really compute intensive. It's compute intensive because I need to inspect every byte of every packet, and because just getting those packets in order in the way that the application would see them is also expensive. So the challenge for intrusion detection and prevention systems today is that our demands for how much data they process is going up very rapidly. What I'm showing here is a graph on the x-axis showing what is considered to be the state-of-the-art line rate by year. And as we can see, today, people consider 100 gigabits per second to be state-of-the-art. And some of Intel's customers who I've been lucky to speak with as part of this center have told me that really they were already working on 400 gigabits per second. So these demands are going up very quickly. They're reaching absolutely astounding rates. And yet, state-of-the-art intrusion detection and prevention systems that run in software can only process about 1 gigabit per second per core. Now, this 1 gigabit per second per core number is a state-of-the-art number from a software system that came out in NSDI 2019 called Hyperscan. And this number already represented a huge leap in our ability to implement intrusion detection, and in particular to implement what's called deep packet inspection, that is scanning through those byte streams in IDSs. Prior to Hyperscan, we were doing an order of magnitude or even 2 orders of magnitude worse. Even with this phenomenal leap though, we're much slower than we need to be. And in our own experiments, we were very rarely even able to get up to the 1 gigabit per second number. We ran Snort 3.0 equipped with the Hyperscan pattern matching library over some network traces from real empirical data sets of different applications, some of which had attacks in them and some of which didn't. To keep up with 100 gigabits per second using this state-of-the-art open source software system, we would have needed anywhere between 4 and 21 32-core servers and thousands of watts to keep up. So what we're looking at here on the x-axis are different network traces. And we're looking at on the y-axis is the number of cores that would have been required to keep up with 100 gigabits per second. And I should note that we were very generous here in this evaluation. We actually only ran with one processor core and looked at its throughput and then simply multiplied to see how many it would take to get up to 100 gigabit per second. That is, we assumed that we would get perfectly linear speedups, even though we know that there's basically no system in the world that gets perfectly linear speedup, and that in practice, we should expect Snort to do at best this well, but most likely require even more cores than the number I'm showing on this graph. To address this challenge, we built a new intrusion detection system called Pigasus. Pigasus uses an FPGA embedded in the server, like the Crossroads FPGA, although since we don't have a physical Crossroads FPGA, we used an FPGA-based SmartNIC. And we built a system that could keep up with 100 gigabits per second using just one FPGA and one 16-core CPU. So instead of needing those 4 to 21 servers, instead we needed just one server. And to be honest, we had room to spare within that server. Maybe we could go up to 100 or 200 gigabits per second. At that point, our packet generator would have been the problem. So we weren't even able to evaluate how far we could take this. The key idea behind Pigasus is that packets are going to come on and off the FPGA, and the FPGA is going to be the owner of all of the packet processing, and that 16-core CPU is only going to help out. So this is what I would call an FPGA-centric or FPGA-first design. Let's compare the results we got out of Pigasus, and then I'll talk a little bit more about how Pigasus works. We said that Snort would require between 4 and 21 servers. And with Pigasus, we required only one server. Rather than needing thousands of watts of energy, we would only need tens or hundreds. So here are the results for the same traces. And note that for some of them, we would need as little as just one core to keep up. And so we have a much smaller physical footprint. We have a much smaller energy footprint. And cost-wise, this is also just a cheaper design. Pigasus is among the projects for the Crossroads Center, one of the more mature projects. So if you want to learn a lot more, over the past year, we've had some big achievements. There's an OSDI 2020 publication that goes into some of the core systems and architecture designs that allow Pigasus to achieve its success. You can read that paper in the OSDI 2020 paper. There's also an open source release. You can go to, actually there's now a macro, you can go to pigasus-ids.org. And go directly to the source code. Extensions to this are being developed at the University of Toronto, University of Virginia, UC San Diego, and the University of Washington. And there was quite a bit of press coverage talking about the world's fastest open source IDS that we had released. Towards the end of this talk and in a couple of slides, I'll talk about some of the ongoing Pigasus development. But first, let's talk a little bit more about the Pigasus release, the source code that you can access here and what we talk about in the paper. We know that Pigasus is much cheaper than traditional software, both financially and in terms of energy. And we know that it achieves this by taking a FPGA first approach. To understand what an FPGA first or FPGA centric approach is, let's talk about a traditional CPU centric approach. In a CPU-centric approach, packets are going to come into the CPU first. So they're going to come off the NIC, they'll zip over PCIe, and then they'll go through some sequence of tasks. The packets will be parsed, they'll be put in order in this flow reassembler, and then maybe there'll be some task that the FPGA is assigned to do. In many of the related pieces of work in the literature, people do the scanning, that is the search through the payloads on the FPGA. In SNORT, that module is called the multi-string pattern matching. And then the multi-string pattern matcher is able to identify packets that are considered to be suspicious. And then a final search that does regular expressions, and some more complex search is done on the CPU that decides ultimately whether or not a packet is an attack or not. And then this full matcher makes the final call. Is a packet innocent, or is it an attack? If it's an attack, it gets dropped. If it's innocent, it's sent out to the network. So notice that a lot of work is done on the CPU. And when I talked previously about the problems with the traditional CPU-centric model, we talked a lot about data bouncing around between endpoints. So we see here that in this design, data is bouncing around between the NIC, the CPU, and the FPGA and back. It's a lot of latency, and that's a lot of data going over PCIe, potentially bottlenecking throughput. In an FPGA first architecture, the FPGA is the main processing unit. The FPGA is on path, it operates on data while it's in flight, and the data is already there. And so the common cases are entirely processed on the FPGA. In Pigasus, we re-architect the design so that when a packet comes in, it receives almost all of the processing on the FPGA. We do the Ethernet parsing, we do the Ethernet parsing, we do the protocol parsing, we put the packets back in order using a flow reassembler, and then we do a first pass search through the data to identify whether packets are suspicious or whether we know they're innocent, all on the FPGA. Packets that are considered to be innocent are shipped out to the network, and packets that are determined to be suspicious are sent up to the CPU, where they incur more expensive processing that does things like regular expressions and more header analysis. In practice with Pigasus, we see that 95% of packets in our traces are processed entirely on the FPGA, leaving only 5% of packets up to the CPU. And that's where our big gains come from. That's why we need so few processor cores to keep up. There's quite a bit of ongoing work on Pigasus. First, we're extending Pigasus right now to do message parsing. Basically, the idea is that Pigasus should be smarter by being aware of different protocols' message structure. SNORT and other IDSs today can do special search that knows that it's looking at HTTP packets or DNS packets and be more efficient in the way that it searches them and more secure in the way that it searches them by looking only within the context of a message for attacks. The Pigasus design right now is not aware of these protocols, so it's a little bit less efficient. And we think we can make it better by adding this pork library that is aware of protocol messages like those in HTTP. Another really exciting result that I'm going to talk a little bit more about on the next slide is our ongoing work on the Surge Protector DOS defense framework. And so the question that we left at the end of Pigasus was, what happens if an intrusion detection system becomes the target of attack itself? We have a large range of experiments that show that if an attacker tries to attack any intrusion detection system, like SNORT, like Suricata, or like Pigasus, it's very easy for an attacker to slow the system down and force the system to start dropping packets from innocent connections. The way that an attacker does this is by mounting something called an algorithmic complexity attack. You basically send packets that are very expensive to process. And so the system spends a lot of time processing the attack packets and then doesn't have time to process the innocent packets, so it drops them. I'll come back to this in one more slide, but I just wanted to also mention some future work we often get a lot of questions about. Pigasus does not support encryption or compression yet, although we're hoping to do that. We're also expecting to add support for QUIC and UDP later. Right now, we just focus on TCP. But let's go back to that denial of service question. We're worried about attackers who attack Pigasus itself and send really expensive packets to process and then slow Pigasus down so that it doesn't have time to work on innocent traffic. This is a graph that I just saw for the first time today. So Nira Batre, the lead student for the project, has now extended Pigasus with a surge protector. And what we're looking at is what happens if an attacker sends an increasing rate of attack packets that are very, very out of order. And so they're designed to slow down Pigasus's reassembler and its analysis of TCP connections where the packets come in out of order or very lossy. And what we see in Pigasus out of the box is that as the attacker increases the attack rate, the good put, that is the fraction of innocent traffic that is processed, goes down very quickly. But when we add surge protector on top, that is Mirov's new tool that prioritizes packets based on how much resources they're using, we maintain a very high good put even while the system is under attack. I don't have time to talk today about how it works, but all I can tell you is that the design does make Pigasus less vulnerable to algorithmic complexity attacks. It uses queuing theory to provably protect network systems. So not only is this code that's integrated into Pigasus, there's also pages of proofs that theoretically show that this is basically impervious to attacks. And this design can be applied not just to Pigasus, but to any middle box, so including Snort and Zircata and many of Pigasus's software competitors. So this is some work in progress that I'm really excited to be able to highlight for the first time today. Now, let's talk about another completely different system, Norman. What is Norman? Well, Norman is a change to the networking stack in operating systems. And unlike Pigasus, a developer who uses Norman probably isn't going to think about the FPGA at all. Let me talk about what Norman does, the problem it's solving, and what our goal is. Norman is very early stage work, so unlike Pigasus, I don't have code to point at. I have one short workshop paper that I can share with you, but this is very active research and very new material I'm going to talk about today. So in a traditional network stack, most popular design today, Linux, Windows, Mac OS, everything kind of looks like this. Packets come in off of the network, and if I'm running a web server or I'm running a key value store, one of these IO intensive data on the move applications, they're sitting somewhere in user space, but packets don't go directly to the application. When they come in off the network, they're handed to the kernel. And the kernel does some nifty work for these applications. They implement TCP. The kernel will do some filtering and security policies. It might do some queuing, and it might even implement some encryption or support for IP security. Much like the conundrum that we were faced with Pigasus, we're seeing NIC speeds go up, but CPU speeds aren't keeping up. And so a huge trend in the operating systems literature over the past 10 years has been complaining that running all of this packet processing on the kernel and running data through the kernel is really slow. And the systems community has focused really on the difference between running this kernel-based functionality in the kernel versus in user space. The systems community has said, look, we want to implement congestion control, we want to implement filtering, but the thing that's slow here is that the data is being copied between applications in the kernel and that we're doing lots of syscalls. And so the big idea at places like OSDI and SOSP and NSDI over the last few years has been to implement what's called a kernel bypass network stack. And the idea with a kernel bypass network stack is that applications will interface directly with the NIC and implement the network stack in a library. So instead of packets going through the kernel, they'll go from the NIC directly to the application. But note that the application is still running a bunch of code. It still needs to implement TCP. It now needs to implement some of its own security policies. But we avoid the additional data movement. This time, we're not talking about physical data movement, but virtual data movement, that is copies and syscalls, about getting the data in between kernel space and user space. This is state of the art. There are 10 million kernel bypass research papers that are published every year. Okay, maybe not 10 million, but I've certainly read a lot of them over the last 10 years. But my own experience and the experience of my students and collaborators in working with kernel bypass systems is that kernel bypass, while it's very fast, leads to a maintenance and manageability nightmare for administrators. And the key problem here is that kernel bypass cannot fully replicate kernel functionality. So to understand the kind of functionality that can be replicated here and where our problems come from, Let's look at an example with two friendly users here. This is Alice. She's a sysadmin and she maintains a server. And this is Bob. He's her summer intern. I feel a little bad. My summer interns are really smart, but these examples are going to show Bob causing some problems for Alice. So let's note that Bob is not a Carnegie Mellon summer intern. Okay, so in this example, we have a NIC, we have a kernel, we have a database. We're in the traditional world. And the database has some very important functionality. It's customer facing, lots of people are using it. Bob, the intern, shows up on his first day and installs this application. And he's sending a ton of traffic. And unfortunately, this is dominating the NIC bandwidth, and there's not enough capacity for the database. And so what we can do in the traditional kernel world is Alice can come in and say, okay, kernel, I want you to prioritize traffic from the database over traffic from Bob's app. And so she can sandbox some of the networking performance for Bob's app to have a little bit of data going through, but ultimately the database is prioritized. The way that she does this is using a tool called TC, which is implemented using QDisk in the kernel. And this is baked in default functionality that every administrator is used to applying in Linux. Yay. Bob sends too fast, the data gets dropped. Now in the kernel bypass world, there's no way to do this. The problem is that data goes directly from Bob's app directly to the NIC, and Alice doesn't have any hooks for this prioritization that allow her to have the privilege and make any changes. Here's another problem. Bob set a weak password and the server got compromised with a malicious web server. And so we're noticing lots of malicious traffic going to and from our server. Alice comes in to try and help. She says, okay, well, which application is listening on port 80? Let's track down that buggy web server. So here in the kernel world, in the traditional world, she can use tools like netstack to look at all of the open sockets. But once again, in the kernel bypass world, these tools aren't here. So Alice is used to having handy tools. And when we get rid of those handy tools, Alice can't handle these problems. She has a lack of kernel interposition. Now, we're not the first to notice the lack of kernel interposition. There is a system that was published at SOSP 2 years ago called Snap. This came out of Google, and the key idea here was that packets from the application will still bypass the kernel, but they'll be routed through a core that is managed by a privileged administrator and then rerouted to the NIC. But if we think about the underlying hardware, what happens here is that this reintroduces data movement overheads. So data is being shipped between processor cores and then going out over PCIe and reintroducing high latency and potential throughput bottlenecks. Another solution that we see coming out of Microsoft is implementing a software switch on the network interface card. Now, this is pretty cool because there are no additional data movements, but the problem here is that the control lies with the hypervisor. And so I can't say things like which application is listening on port 80. I can only say which virtual machine is sending traffic out over port 80, which is not the same thing. I really want control at the OS level. So what do we really want? We want something that acts logically like the kernel network stack, where the operating system is privileged to interpose over data going in and out of application and set policy. But we want it to be physically like kernel bypass, where we're not copying data around, it's not moving between multiple process endpoints, and that the data goes directly from application to NIC very performance efficiently. So this leads to an approach that we call kernel on-path interposition, which is the key idea behind Norman, our new data plane for Linux that is going to make networking much faster while still providing the same functionality that we get from traditional kernels. And what we're going to do is we're going to leverage the Crossroads FPGA to implement a network data plane that is both on-path, but logically controlled by the kernel. So here's what that's going to look like. We're going to have a server that has an FPGA and a CPU, and the kernel has the control plane, and it can install code on the NIC to define the data plane functionality. I like to think of this very much like when I install my operating system today, it asks me what kind of file system I would like to lay out on the disk. In a KOPI design, when you install your new operating system, the operating system is going to install a KOPI data plane on the FPGA. That is, the operating system is going to ship with RTL that defines how congestion control works, or that defines how a queuing discipline works. And this is all going to be programmed onto the FPGA at installation time. Now, this is really important that the kernel can make changes to the data plane using code. There are a lot of systems out there, a lot of hardware systems out there from many manufacturers that offer functions like TCP offload or that offer functions like encryption. But these designs have been soundly rejected by the operating system community because they like to be able to update things. In the Linux kernel last year, there were over 377 commits to the NetFilter library. And so if we want to be able to make these changes to the networking stack on the fly, as we're used to, our data plane has to be programmable. And that's why we want to use an FPGA rather than some fixed function SmartNIC that comes to us with encryption implemented or with TCP implemented, provided to us by the manufacturer. The kernel should be controlling the code itself. Okay, so now when the kernel controls the FPGA, what happens with applications is that the application now has a split interface. The application is capable of talking to the kernel for control plane operations, but for data plane operations, that is when packets are coming on and off of the network, the application just talks directly to the FPGA. It talks directly to the NIC. And so when packets come off and on, physically, they're receiving the same performance as kernel bypass, but they're still getting all of the interposition, all of the functionality that the kernel would normally provide, because the kernel has installed that code onto the KOPI data plane on the FPGA. Now, once again, because we don't have a Crossroads FPGA, we're using a SmartNIC. Norman OS is being built to use a SmartNIC, and it implements the kernel functionality and a special library that the app uses to interact with the kernel on the control plane and with the KOPI data plane on the FPGA. The KOPI data plane is responsible for things like filters, queuing disciplines, and packet sniffing. And the library that allows the application to talk to the KOPI data plane doesn't do any sort of interposition. It doesn't ship things to the kernel. It doesn't do any interrupts. It doesn't do any copies. Now, on the kernel side, the kernel is responsible for control plane operations. And so this is things like a user might say, oh, please install this rule with IP tables. Here's something I want you to filter. Or my administrator comes in and says, here is some data I want you to prioritize. I'm going to talk to an application like TC, and then the kernel will tell the KOPI data plane, data on this connection is more important than data on that connection. Okay, so let's summarize KOPI. KOPI observes that kernel interposition is essential. We want all of this functionality that the operating system gives us for our application. And using the KOPI architecture to leverage a Crossroads FPGA gives us a path to restore interposition without reducing overheads, or without reintroducing overheads. So there's a paper about this that appeared at Hot OS this year. It's more of a vision paper. The code is not open sourced yet. We are working on a paper submission towards the end of this year, but we're actively looking towards feedback and people who have thoughts about our design, because this is much more of a work in progress. Now, before I conclude, I just want to look back at both applications I've talked about. I talked about Pigasus and I've talked about Norman. Pigasus is an FPGA-centric design. The Crossroads architecture enables us to design a new class of systems where the FPGA is really owning the processing, and it uses all of the rest of the system resources, including the CPU, as helpers. But it doesn't have to be that way. Norman is a much more CPU-centric design. We want to run traditional applications. We want to run traditional web servers, traditional key value storage, deep learning frameworks, whatever. And we're just pushing their networking stack onto the FPGA. But it's the CPU that's telling the FPGA what to do. And so in that regard, Pigasus and Norman and the KOPI architecture that it implements represent very different design points, even though both of them make heavy use of the Crossroads architecture. In the future, both of the applications I've talked about are network-based, and that's because I'm really a networking person. But we're curious about how the Crossroads architecture can help other domains. For example, what's the KOPI equivalent for file systems? If I have data coming in over the network or coming from the CPU that wants to go to disk, what do we want to do there? And given the applications that we build, we've focused entirely on an FPGA, but perhaps we want some sort of hearted compute resources also embedded in the Crossroads platform. This is an open question that's been coming up over and over again in our meetings. And so I suspect that some of the application design questions that we've been talking about will lead back into new hardware design questions. Okay, with that, I will take any questions. My email is here. Thank you very much.